Welcome guys, back again to another video. This is our photochemistry video series. If you have not watched our previous videos, I highly recommend you to watch it. You can watch it through our playlist. So in this video, let's talk about the quantum yield, which is a very important concept in whole photochemistry and photochemical reactions, right? So let's start over with a quick example, right? So you know this energy diagrams, right? So here we have the ground state, here we have the S1 excited state, and here we have the T1 triplet excited state, right? So when it comes to photochemistry, there are so many processes, right? So there is a excitation, okay, intersystem crossing, okay. So if we are going to introduce another excited state, there's a internal conversion. Likewise, there are so many processes: fluorescence, phosphorescence. These are so many processes, right? So quantum yield, right, this quantum yield specifically target a specific process, right? So let's say you need to find a quantum yield, you need to find the quantum yield for this intersystem crossing process, right? This process, for this process you need to find the quantum yield. Now what you need to do is, okay, the quantum yield, the symbol is psi, so you need ISC, which means the quantum yield of the intersystem crossing. The expression is given by the rate of the intersystem crossing over rate of excitation. This is the expression for quantum yield, right? So rate of the intersystem crossing is the basically the rate of this particular step. So if you are going to let me draw it here, okay. So here we have the A molecule, which is on the S1 state, right? S1 state. So it's going to be converted into the A triplet state to the intersystem crossing. So let's say the rate constant is K dash, okay, K dash. So now I hope you know how to write the rate of this particular reaction step, basic kinetics, okay. So the rate is given by K dash, the rate constants, over the reactant concentrations, right? So here we have the A S1 concentration. So this is the rate. So you can substitute this particular expression for this place, and rate of excitation. The excitation process is the here. The ground state is going to be excited into the singlet excited state. That's the excitation process, excitation reaction. So you know this is not allowed, right? This excitation is not allowed. We have to talk about the reason why. So we are not going to be considered this particular step unless the particular problem given us the specific guidelines for there is a excitation from S0 to T1. Otherwise we are going to neglect because it's not allowed. Now when it comes to the excitation, what's going to be the rate? The reaction is A from the ground state to the A S1. Let's say the rate constant is K star, okay. Now I hope you know how to write the rate expression. So the rate is K star over the reactant is this one. So here we have the rate expression concentration. So you need to substitute the rate of the specific process which we are looking at. In this case it's the intersystem crossing. So here we have obtained the rate expression for it. That's the rate, and rate of excitation, right? Rate of excitation, which is this one. So let's do a quick example to see how we can apply this quantum yield in practical manner, right? So here we have a problem. So you may see, like, you will see it little bit complicated, but hang on, this is not a big deal, right? It's just a symbols, okay. So let's first look at what happens in here, right? Okay, so here we have the irradiation step, okay, irradiation step. Here you have the A molecule which is in the ground state, and here we have the excited A molecule, and then here we have the excited A molecule is going back into the ground state, and here we have the excited A molecule, okay, which is going back to the ground state through the emission. These are specific processes, right? There are different processes which the reaction may happen, fluorescence, phosphorescence, likewise. So these are particular processes. So here we have a reaction here. This is the excited A molecule with another B molecule, right? It's going to be form a radical mixture. Okay, radical mixture is going to be formed, and here again this radical mixture is going to form a ground state A and B. Okay, and here we have finally the product formation. Now in our first question, okay, we are asked to derive an expression for the quantum yield of emission from excited A in the presence of B. Okay, so we are going to derive an expression for the emission from excited A in the presence of B. So here we have the emission. Sorry, it's not here. Yeah, here we have the emission. This is the emission reaction. Ke, which means that this is the emission reaction. Okay, now we are going to apply our known quantum yield knowledge. Okay, we are going to ask the quantum yield. So this is the quantum yield. In this case, you have the specific rate, which is going to be the emission of excited A. So the rate of emission. Okay, over the other one is constant, rate of excitation. This is the expression, right? This is the expression. So we need to find the expressions, rate expressions for these particular steps. Now let's move on. Okay, let's see how we're gonna do it. First of all, let's write the expression for the excitation. Okay, rate of excitation. Let me do it. So you can see here, this is the excitation, right? Sorry, here this is the excitation. This step, this is the excitation step. So you can see the rate is given here as IA. IA is the rate. So as you can see that this IA is already contained with the particular constant and the concentration, right? So you don't need to introduce a new rate constant here. This IA just the whole expression. So rate of the excitation is just the IA. Now what we are going to need is the rate of the emission, which the rate of interest of ours. So here these are the processes which are involving in our reaction. Okay, let's see how we're going to do it. So now I'm going to introduce the expression for rate of emission. Okay, for the rate of emission, you can see here, this is the step. Okay, this is the step which we are going to focus on. So let's write the rate expression for based on that step. We have Ke, the rate constant, and the excited A. This is the rate expression for the emission process. Now look at this very carefully. This excited A over here, it's not in our initial mixture, right? There is B in our mixture, there is B and there is A. That's all. Right? So you cannot put a expression based on this excited A, right? You need to derive your expression back to A and B and these given data, IA, KD, KE, these are the data. So this excited A concentration is not given to us, right? So you cannot put excited A concentration in your expression. So let's substitute for this A. We can do it, right? We can do it like this. Let's see, D capital A star over dt. So here what I'm going to do is I'm going to derive an expression for the rate of the formation of excited A. So let's just do it. Here I'm going to introduce the expression for the rate in the formation of excited A, right? So you can either derive expression for the dissociation of excited A. It's completely fine. Only difference is you're going to completely opposite the but the positive and negative marks. That's all change. So let's go with the formation of excited A, right? So let's here. The first step is here. Let me take a good color. Okay. First step is here. Formation of here. So IA is there plus, and then we have a dissociation of A. So which means it's not a plus, it's a minus, because we are talking about the formation of A, right? Yeah, we are talking about the formation of positive A star. So in this case, A star is diminishing. In the second step, A star is diminishing. So it's a negative KD over A star. KD over A star. And let's look at the next. Another diminishing step, which means a negative KE A star. And next one also another diminishing step, right? You can see here A star is diminishing, it's reducing. So you need to add it through a negative KET. Here you can see in this step, look at this. Here you have the rate constant and you have two reactants. So you need to add both, right? A star and B. Now we are going to do an assumption, right? Our assumption is at steady state conditions, which means like our system is now in an equilibrium, right? So the rate of formation of A is going to be 0 at the equilibrium. So like there is a no net change in our A star, right? So let's say if I explain it to you like this, there is a star in our mixture, right? So let's say there is 2 moles of A star in our mixture. So when it comes to all the kinetics, for every 1 second there is a 1 mole of A star is forming and 1 mole of A star is diminishing. So if I ask you a question like what's the net rate of formation of A, it's 0, right? Because 1 mole is forming and 1 mole is diminishing. So the overall with the time, the 2 moles of A star is constant. So there's no net change in A star. So this derivation term is going to be 0. So I can derive the expression based on that. We have IA negative KD A star negative KE A star negative KET A star B equals 0. Let's introduce the terms. IA equals KD A star, those are in here, KE A star KET A star and B. Okay, now you can take out the A star terms out. KD plus KE plus KET and B is inside, and A star is going to, I'm going to take A star out, and here we have the A. Now we are going to move this whole term across the equal sign. IA over KD plus KE plus KETB. This is equal to A star. If you remember, we have here derived the expression for emission. Only problem was we didn't know the actual value for A star. Now here we have obtained a expression for A star using like the B concentration, Kc, Ke, Kd, all of the data they have given us. So we can substitute this A star expression here. So let me write it over here too. Rate is equal, here we have Ke Ke and then A star term here, Ia Kd plus Ke plus Ketb. Here we have obtained the rate for the emission. So you can see it's not a big deal, right? It's not a big deal, even though the question is giving you like whole lot of informations and lot of symbols and stuff. That's a not big deal. You just need to look at the two processes, right? No, one specific process which they are asking of you, right? In here they are asking for a derived expression for the quantum yield of emission from excited day. So look at that particular step right here. Look at this. This is the particular step. This is the emission step. So introduce a rate expression for this particular step. Okay. Introduce a rate expression for this particular step, which is Ke over A star. Now you don't know the A star here, right? A star is the excitation state. So you don't know the concentration for A star. Now you need another expression to obtain the expression, obtain this A star value. So what you're going to do is you're going to introduce the rate of formation of A star. That's all. Okay, that's all you're going to do. So you're going to derive the expression. You're going to see only the steps which are affecting this A star concentration. As you can see, I have taken this step, this step, this step, this step, but I haven't took these steps because there is no A star involved in these reactions, right? So A star is independent from these expressions. So I only need these four expressions to consider the A star concentration. Okay. So I have derived the expression here, and then I have applied the steady state theorems, and then I have obtained a value for A star. Now I have the A star, so I can easily replace A star for this rate of emission. Okay. Then here I have obtained the rate value. And then if you are gonna if the question asks for like the quantum yield for the emission of A, so here you have the rate expression for the emission of A, right? So here we have the rate, this one here, over rate of excitation, which is Ia. So Ia is going to be cancelled out. So here you have the expression likewise. So now our first part is okay. Now let's move on to the second part. So here we are going to ask us, show that the quantum yield of the reaction is given by this whole expression. So now they are going to ask about the reaction, right? So this is the reaction. Let me take the color. Okay, here this is the reaction now, right? This is the reaction. So they are asking for the quantum yield. Look at how I'm going to approach this problem, right? Just take the concept, then it's pretty much easier. Okay, here look at this. They are going to ask you about the quantum yield. So I'm going to take the quantum yield expression. So the expression suggests the rate of interest, that step. So they are asking for the quantum yield of the reaction. So this step. So you need the rate of this Kr step. This step, the rate of this step is needed over rate of excitation. We know this, right? It's just Ia. We only need to find this Kr step. So let's move in. So how we gonna approach this? Okay, I'm going to write a rate expression for this final product formation step. Rate of the product. Rate of the product formation. We have Kr. Okay, and we have two reactants here. You can see A plus star, A plus radical and B minus radical. So both of these concentrations are involving in our reaction, in our whole reaction, right? So now another problem rises. We don't know this one and this one. So you need to have a expression for both of these. Now look at this, the same thing which I have done here, right? I need a concentration for both of these. You can see like both of these guys stays fixed, right? So like there is no a radical independently present in anywhere, right? So I'm going to introduce our formation rate expression, right, like this. both of these guys, right here, look at this, both of these guys, dt. So now I'm going to introduce the rate expression. Okay, here d a positive minus b negative over dt. So I'm going to look at the formation of these two, right? So let's see which reactions are involving in these two concentrations. Here we can see three reactions. This one, there is the formation of here, and there's a reduction of our guys, and another reduction of this guy. So three reactions are involving with the concentration of our desired products, right? So we only need to consider these three reactions. We don't need any other reactions. So let's move on. So let's look at the first one. Here it's a formation, right? So we have introduced our rate expression for the formation of both these. So it's a positive because it's a formation. And now KET, there's a two reactants, KET, and two reactants are A star and B. And then there is second reaction step, which is a reduction step. I mean, reduction means like the reducing of these particular concentrations, right? You can see these radicals are going back to the A and B. So the concentration of A radical and B radicals are reducing. So when it comes to the rate formation, it's going to be negatively affecting. So KEBT is negatively affecting it. KEBT, A radical and B radical. And there's another step, final step, which is also a reducing step to products, KP, right? Yes, KR, sorry. It's KR, negative KR over A and B. Now, just like before, I'm going to introduce the steady state theorem by applying these guys to 0. So now we have 0 equals KET, concentration of A star, concentration of B, negative KEBT, concentration of A radical, and concentration of B radical, negative KR, concentration of A radical, and concentration of B radical. Okay, now let's move these guys to the other side. So we have KET, A star, B equals KEBT, A radical and B radical, plus KR and A radical and B radical. Okay, now you can see these two are common for both terms, so you can take it out. KEBT plus KR, A radical and B radical. Okay, so KET, A star, B star. So now what we need is, initially you can see here, what we need is an expression for these terms. So here you have these terms, so just move these guys across here. So yeah, let me take another, sorry, let me take another slide for it. Okay, okay, so now I'm going to move these guys into the other side. So we have the expression like KET over A star B, A star, and we have B over this guy KEBT and KR. Here we have the KEBT and KR, okay, equals to our radicals, A radical concentration and B radical concentration. Now here we have the rate expression for our desired step. So what you need is, you need to substitute this expression in here, okay, in here. Now after the substitution, so let's substitute it. Rate equals KR KET A star B over KEBT plus KR. Now the problem, another problem rises, right? Here you can see A star, yeah, A star. This is not initial data, right? Initial data which you have given. So you need expression for A star. But if you remember previously, we have derived expression for A star here. We have derived it in our previous step. So you can substitute this A star to, now you have the whole rate expression for this particular term, right? You have this term. So the rate of factorization is also there, IA. Now they are asking for 1 over QR, right? So you just need to turn upside down. So you will get the answer. So I hope you get the idea. This is the concept, right? So most of these problems are similar to these patterns, but take the concept. So whenever they are expressing, like, they can introduce the fluorescence, phosphorescence to this, right? So they can be asked for like quantum yield for the fluorescence, quantum yield for the phosphorescence. In what case, any case, what you need to do is you need to identify the specific step, right? And then write the quantum yield expression. So then you already know the rate of excitation, it need to be given. So you need to find the rate of the desired step, right? So when you find the rate of the desired step, you will see that one of the concentrations may not be given as initial concentrations, right? So you need to find another expression for that particular species. So you can apply the steady state theorem for that, and then you can get the expression. So it's try it yourself for several times, then you will be fine with it, right? So I hope you're okay with it. If you have any problems, please feel free to comment below.